Okay, I think we can start the first talk in this room called Happiness. What a lovely name. So without further overdue, our first speaker's list of achievements is impressive indeed. PhD from Utrecht University, 2 books written and published, Practical Haskell and Book of Monads, or I should say the Bible of Monads as it's called, both within 1 year. Then we have another book of his, Beginning Haskell, written a few years earlier. He's also the member of a member of the GHC steering community. And I don't know how he finds time for all this. It's impressive. And today we'll have the opportunity to hear him talk about GraphQL language in the context of the rising star of Haskell's web libraries, Mu. So ladies and gentlemen, Alejandro Serrano.
Thanks very much.
Before you start, I'd like to tell you that Alejandro will be taking questions after his talk in a special room, which I'm sure you have linked to. Alejandro, the audience is yours.
Yeah, thanks very much. Somehow I was somehow picturing that this was like, this Eurovision contest. So, like my 12 points go to Haskell. So that's, I don't know. I was just pop out randomly in my mind. So I just thought, let's share this. But yeah, thanks for the introduction. My talk is indeed about GraphQL and how we built a library to work with GraphQL in Haskell. So, roughly, you may not know what GraphQL is, so I'll introduce this during the talk, and then I'll talk about Mu, which, as you've said, is a library to make microservices in Haskell. We've been developing this at 47 degrees. That's where I work for a while. And we recently added GraphQL support because that's something that my colleagues and me are very excited about. So let me yes, I said first say what GraphQL is, and maybe this QL already reminds you of query languages, and that's indeed what it is. It's supposed to be a query language, but for APIs. So it originated in Facebook, but now it's like its own thing, and it's intended to replace REST for web APIs, and I'll shortly explain why the creators of this think that this is going to replace REST. And Mu, that's the library I've been talking about, is sort of a framework to build microservices in Haskell, but also in Scala. So that's something we try to develop at the same time in both languages. At 47 degrees, that's where we mostly use it, although we have some outside contributors. Everything is open source. And we try to support a wide range of protocols. So we support gRPC, we support Abro, and recently we added this support for GraphQL. So the idea of GraphQL is that instead of just having an endpoint, you describe what is the exact data you require. So imagine I have this query I'm showing right now on screen. What I'm asking is, well, give me all the authors, but I'm not just saying, give me all the authors. I'm also expressing what I want from the author. So I want the name and the list of books, and from each list of book, I want the title. Of course, authors may have more information and books may have more information, but I'm explaining within the query what's exactly what I need. And the result is just going to be, your typical JSON document, but it has exactly those keys and exactly that amount of data. So it roughly looks like that. So you have always a top level key data, and then inside you see there is authors, and then that's an array. So for each author, you have the name and book, and well, here a couple of writers I like, because you express exactly the query you want. GraphQL servers, as opposed to REST, usually expose one single endpoint. So essentially, your different REST queries become different top-level queries in this thing. So here I have authors. You can think of this as, the / authors you get. and maybe you have something to get one specific author, so it will be the top level thing there. Now, as I said, the idea of GraphQL is to express exactly the data you require, and that prevents both overfetching. So imagine I just did this in REST and I'm not able to express exactly what I want. I mean, I'm saying REST, but this also will hold for other RPC mechanisms. The thing is, because you cannot tell what data you require, you might get more information. So maybe you ask for the books from an author, and then you just need the title, but then you get the title, the number of pages, and the publisher. And that's all information that we have to get from the database in our server, but also bandwidth we are sort of wasting for things you don't really need. And the converse is also a problem. Sometimes when you use this kind of APIs in REST, you need to do several queries and sometimes even n queries to get all the information. So imagine that here I would have an author's endpoint, which gives me like the names and identifiers and information about the author, but not the books. And then for each author, I have yet another endpoint to give the books per author. But if I need to get the first 10 authors, let's say, I would need to make then 10 queries to the books endpoint, which means I need to do 11 queries to do this, which is, of course, a loss of time and bandwidth. The downside of doing this, the downside of having this sort of more complex query language is, of course, that, if you try to write the code for the author's endpoint in REST, that's going to be like a simple query to your database, and also for the other one, so you check that the ID is correct, and then you go into the books table, whatever. But now this becomes way more complex because you have to go down and inspect the query. So because of this, there have been a bunch of frameworks. So GraphQL actually was originally introduced in the context of React, this JavaScript, TypeScript, Reason framework for developing web frontends. And still sort of the JavaScript Node ecosystem offers the more complete solution. So there are several client and servers, but there are many choices for other languages. And one thing which is quite exciting, at least for me, is that most of the languages where GraphQL have found its way and you get nicer APIs are actually functional languages. So you have Absinthe for Elixir, Sangria and Caliban are for Scala. You also have one for Python, Gefreen. But as I said, Elixir and Scala showcase how you can get very nice APIs for GraphQL for building GraphQL servers when you have a functional language, because I think they fit quite well. Now, this GraphQL things actually comes with the schemas, and I also like it because being a Haskeller, of course, I like my types. So, why not have types for the data I want to describe? And that's exactly what these GraphQL schemas give me. So in the previous case, for example, that will sort of be the schema. That's quite long. I'll just shortly talk about the different things. But you can see that essentially you have two types. We have the type of books, the type of authors, and book and author have some piece of information. And then we have a type of queries, and that's one specific GraphQL thing. So the query is itself a type. And you can see that we have authors, which have a name, which may not be present, but you can have a default value, and the same for books. And using Haskell notation, the list is also written between square brackets. Now, focusing a bit more on the GraphQL schemas, we have here books and authors. And in order to read this type, the main thing you have to remember is that the bank means required. So I always put a bank everywhere because why would not make this thing required? And then the angle bracket means a list of. So you can see, for example, there that in the authors type, the books field is a required list of required books. There you have it. But interesting, relations in this language are expressed directly as children. So we see here that book have an author as a child, so as a field, and author has books as a child. And you might wonder, why don't we go into cycles? I mean, we can go and ask for the book, then ask for the author of the book, then ask for the books of the author of the books, and then ask for the author of the books of the author of the book, and so on, and keep like going indefinitely. Now, actually, this is the reason why this is not such a problem here is because remember that we are always being very explicit in the query, which means that we always say how far we want to go in the query. So we could ask for the book, and then the author of the book, and then the books of the author of the book, something like this. But you're always sort of saying how far you may go. Although I wrote an asterisk because using some further functionality in GraphQL, you can actually create a query which results in a cycle. So, but if there is a cycle in the query, this is by the spec. This is forbidden. So, I mean, essentially, if you refer to yourself, and there is a thing called fragments where you can refer to yourself. If you refer to yourself directly or indirectly, then that essentially that's a malformed query. So you don't even try to do this. Now let's go to Mu. So I've been talking a lot about GraphQL. I hope you now got an idea of what GraphQL is and how it looks like. So let's go into Mu. So this is how you start using Mu. You call this GraphQL template Haskell builder, which creates a library. It creates a type for you in this case. So that's from a file. So you take the library.graphql schema. That's your GraphQL schema, and then this GraphQL thing parses it and creates a type in your project. In order to do this, it needs, template Haskell. That's sort of the meta programming functionality in Haskell. So that's essentially how you can write code, which writes code. So GraphQL is one template Haskell function, which just reads this thing during compile time. It performs in I/O. It parses the entire thing, and then creates a type, and this type is called library because that's the one I'm saying. You also need to enable like other 1,000 extensions. So I'm not overly cautious with extensions. I like many of the functionality that we get from extension, and I think actually, and I will talk at the end about why we use this. I think that in this case, the way we use extensions really have a benefit on the type safety on our code. So we create microservices, which at this, that's what I think are you can ensure many invariants of how these things look like. But anyway, I mean, what I like, and that's actually one of the things we're most proud in the while developing the library is using this idea. I don't know where we got it. That types are already there for many things. So we have GraphQL schemas, but if you are using protocol buffers and gRPC, you have also a schema there. And if you're using Kafka, you have your Avro schemas. And if you are developing a REST API, maybe you have your Open API description. So why make the life difficult to people by having to repeat this thing and re-encode this thing in the language? Well, we say no. Let's just bring these things directly into the language. Actually, this is one of the core ideas that we fulfill with this sort of type level schema. So what we do actually is to represent this schema definition in a uniform language. We have like a language which try to encompass a lot of different service definition languages. So we have gRPC, as I mentioned, GraphQL, Arrow right now. Within that we can represent other languages, but of course there is always some subtlety that sometimes make us refine this thing. But the core idea of this is that by representing this schema at the type level, which means at compile time, the compiler can get this information and ensure that everything checks. And as I said, we try to support schema definitions which are already available. So what I think and what for us is most beneficial is that means that there is usually a single source of truth in our polyglot projects. So imagine you have a microservice which is using some you want to do your GraphQL, and then you have a microservice and you develop this in Haskell, but then your Scala consumer can take this schema directly, not to write again and create a client for it, and your React frontend can also take this schema directly. So that means there is a single source of truth, and we think that that's nice because nowadays projects are becoming more and more polyglot. So you really want to have one single source of truth here. And the second thing is also that if you keep this thing in a shared repository, and you may have seen movements nowadays in industry to have like schema repositories, like Confluence schema registry and things like that. You can just, when you compile your code, get the last version and check that everything is still compiled. So check compatibility automatically, which we think is quite nice. You could imagine having a CI pipeline where something changes, then the whole thing is recompiled, and if there is a problem, maybe you shouldn't change your schema before you update all the server code. Well, going back to this, so after my rant, I said that it's like Eurovision, so there is always like a rant before the points. If you don't know what Eurovision is, have a look at Wikipedia. That's an incredible, crazy thing that happens every year in Europe and Australia. But going back to this, let's talk about now how we execute the GraphQL query. So we could have a direct approach, and I mentioned that's how you can just do this. You have a query, and you represent this query using some language, and then you get back, a JSON value, that's the JSON we want to spit at the end, or a list of errors. That's because GraphQL allows you to return both things at the same time. So it might be the case that you were able to get some information, and then there is a field which you've been asked which doesn't exist. So you can still give back as much as you can and have an error. So that's kind of an interesting design choice. So you can get partial data, which you suppose is correct, and then some errors. However, doing this is often complicated. So what we do is we define execution by means of resolver, which essentially mean how you get the value of a field given the value of the parent. So for example, how you get the title of a book from the book, or how you get the books from an author from the author. And by putting these kind of things together, this very composable thing, so again, very, very functional in nature, you can build your whole server. Now, something we're not expecting for sure is to see JavaScript code in a Haskell talk, but I think it sort of allows me to explain some things I need about resolver without having to deal with types, which is going to be at this point really painful. And I'm gonna show you. My goal is to show you why we need to inflict this pain of us for a bit. It's going to be nicer at the end, but we need to do this for a bit. So as I mentioned, the idea is that you have these resolvers which tell you how you get one level, so one field. So we have the query, and essentially the authors allow, so you get some arguments which will have the name. So everything is very dynamically typed here. So the args just come into an object which will look, you need to know the name of the arguments there. And you ask, well, find authors like. And this will give you some list of things. And in particular, we're going to encode an author like the thing I'm showing below. It's going to be an object with an ID, which is going to be a key and a name. So if we want to get the name of the authors, what we do is just get the name from that thing. And for the books, we're going to try to find the books by this ID. And now how books look like is, again, an ID for the key, an author ID for the author, and a title, which is going to be the string. So again, if now we want to have the resolvers for book, well, the title is already there, but for the author, we need to give a book. So the important thing here is that actually we've implicitly defined a type which we use to communicate between the different resolvers. So the query has to produce an array of something of exactly that shape of this author with an ID and a name to be for the resolvers afterwards to make sense, because the resolvers built upon those things. But that's a choice we make. I mean, we could also say, no, our author information, the thing we use that goes around our server, is just going to be an ID, and then on the name resolver, on the resolver for the name field, we query the database at that point. So you can see there is a choice there. So in this case, we are keeping this choice implicit, but spoiler alert, we're gonna make this explicit when we do Haskell. So that's essentially the key idea that we need to make this thing from implicit to explicit, and the reason why we need to make a choice is because there are different ways in which we could express this thing. We could make our thing just have an ID, or as we said here, have some pre-computed amount of values. So let me show you an example of the execution, and this is gonna work the same in most frameworks you use for GraphQL. So I mean, even if you are later you want to go and use the Python version, this is something you've learned and you can go. So essentially here we execute the authors resolver, and we as we said, args.name have the value for that argument, which in this case is not given. So it gets the default value that's in the schema, and the result is a list of objects with these two keys, IDs and names. Then for each element in that array, we execute author.name. So the result is a scalar, is just a string. So yeah, you are done with that field. And for author books, you get a list of IDs, author keys, and titles. That's for each element in your authors array. And then for each element in your books, you execute the book.title. So that gets this triple of ID, author key, title, and extracts the title. So as I said in Apollo, that's the JavaScript framework I was using in the example. The communication between resolver was implicit, and that's something you often see in dynamically typed languages, that you have a structure, but that this structure is sort of implicit. There must be a structure because you need to communicate between different parts of your program, but this is never made explicit. Now in Mu, we must be explicit. We have to give a shape for these things. And we do this by, just creating the types we want. So in this case, we are just copying the code I've defined. So the author, it's just the ID and the name, and the book is the ID, the author ID and the title. And then you have to say, how you map each service type, each type in your GraphQL schema to these intermediate types. So this is what we call an object mapping. And it looks like you're using strings. I'm gonna go deep into that but that's actually going to be a type level string. So everything here is going to be checked at compile time. It's not something that randomly pops there. So book and author really have to be types in your schema, and the ones between quotes, and then they map to the intermediate type you use. Again, I want to stress that this choice of how you use your intermediate result is completely free, and you had more choices, and that's why we have to give you this choice, because in different scenarios, you may not want to pre-compute the name of authors or the title of the authors beforehand. So, for example, here imagine we have a pages field in our book, which most people don't want. So why bring it directly from the beginning? The best thing is to just keep the ID, and if somebody asks for it, then we go to the database, because we expect this to be a best thing. These resolvers afterwards, they are just functions. They are just functions which, given the parent, so this intermediate type, gives you back the field you need. So for example, the resolver for the title gets a book being this type you've defined as being the intermediate type for the book in your schema, gets these books and extracts the value. In this case, it's just called the accessor book title, and you are done. Because in many cases, we want to do some I/O, we want to go and talk to another microservice, we want to go to our database, these resolvers are actually allowed to make I/O. We define our own server error I/O, and we actually got this idea from Servant, which is a great framework to do the same kind of thing, so very type safe services, but for REST. So that's like something where you actually define your web APIs as a type, and then your servers are type checked and type safe and so on. So we got several ideas from Servant, because it's a great project which has been a great inspiration for us. And one of it is, it might look terrible, but at the end of the day, if you are defining this kind of services, you mostly are going to talk to a database. So it makes sense to just expose something which can do I/O directly. And we have this server error I/O, which is essentially an I/O which where you have the extra ability to error with some predefined set of server things. So, like unauthorized, unavailable, these kind of things. So essentially that's what it is. Although the whole framework itself is agnostic of the monad you use there. So so I'll show at the end a very small example where you can add more things by changing the monad there. But going back here, our resolvers may perform I/O. So you have the book author, which in fact, given the book, goes into the DB, runs something on the DB connection, and then gets the information from the author we get the book author ID, and then we get whatever information is there. This is some pseudocode. Like I have a full example. I can give you the link later on using persistent. That's just like a pseudocode, because I don't want to have just a big chunk of code for showing this. In general, actually, resolvers in Mu have this form where you have like a mapping object, and then the arguments, because remember that things like query get arguments, so they are passing extra arguments, and then you have to give back server error IO or any other IO compatible type of the type of that field. So this is the how you get from the schema to the resolver. It's like a not actually a one-to-one mapping, but essentially you always follow the same idea. You get the mapping object, which may change that. That's why it's not one-to-one with the schema. You have the arguments, and then you have to give the field type. So I think it's as simple as it can get. And again, this idea of encoding things as part of the argument as part of the type, it's due to Servant, which I think has been the flagship in doing these things, this type safe, type level oriented services in Haskell. And when you're done, when you have all the resolvers, you go and compose your entire resolver, so your entire server, by giving all the resolvers. So you essentially have to say, okay, this field is this book title is the resolver for the field title in the object book, and the same for each of them. And if you compare this to the JavaScript version, that's slightly more verbose because you have to have object and field all the time there. That's, well, because we have stronger types, and there you just have like a JSON, like an object definition of all your things. But what we get in return is that we check that this server you've defined is exactly a server for the schema you gave us. So you check that everything is there, that everything has the right type. So you will never ever get a conversion error in the middle. Somebody pop up randomly. Good. So going back here, yes, as I said, this is something you get, and well, let's continue. I'll get back into my focus moment. Yes. So yeah. So I mentioned that this server is essentially how you put together all these resolvers, and you can see that this is the core of where we bring type safety to these GraphQL definitions. So this server has a bunch of type arguments, but they all make sense. I'm going to try to make sense out of them. So library was the type representation we brought. Remember this very initial GraphQL call, which defined using template Haskell a type which represents your GraphQL schema. So it's there. That's a server for the library schema. Then we have object mapping, and this object mapping, remember, that's how we define the intermediate objects for that go around our server. So what should we get when we need to provide an author or a book, and what we consume when we need to get a field out of it. And then we have this server error IO, which controls the effects. And as I mentioned, we want to perform any IO, we can stop with server error. That's what server error IO does for us. But in general, you can have way more things, and I'll try to make an example later. There are others, I and underscore. We can talk about them later in the chat, in the Q room if you want. But you know, it's extra information that you need, because actually these servers may come with instrumentation, hence the I, and the underscore is just a trick we play because we need to keep track of something more for the whole thing to work. But actually the thing we keep track can be inferred by the type. So by having an underscore there, we just say, you know, whatever. You know what it is. I don't want to say it's a super big type, but you know what it is. So I'm not going to worry about that. Good. Let's go back to some problems, and that's where I need actually help from the audience. I mentioned that in GraphQL and in most of these frameworks, and definitely in Mu, each resolver is executed independently. So you don't do repeated queries to your microservice anymore, but within the server, we still do repeated queries to the database. So we sort of move the problem from client to server. And there are different solutions in the JavaScript ecosystem. There is something called data loader, which is similar to what Haskell provides in Haskell. And there is join monster, which is something I really love, which is something which creates the perfect SQL query using a bunch of joins are select. So essentially you say, you know, this in part of the database, this is how this relation is encoded in the database. And then it creates a huge thing, like a huge SQL query, which selects exactly the data you want from the database. So it's like a perfect SQL query. And that's what I would love to do. I would like to implement join monster in a type safe way. So really, if you want to see some feat, what I think is a feat of nice API for this kind of thing, look at Join Monster. I would really love to implement Join Monster in a type-safe way. I've given a bunch of attempts. I've tried to use something called monadic lenses. So it's like lenses where you perform monadic things. So that's how you bring things. I've read a few papers by and a thesis where they make lenses to generate SQL. So there's, but this is really resisting me. So I would really love to implement this in a type-safe way. And given that we have a lot of Haskell wizards today, both in agenda and in our chat, it would be lovely if we could find a solution for this. I mean, I would be pleased. I will write the code afterwards if you give me the idea. I promise. Going back to what Mu does, it also supports some other features of GraphQL. One of them is streaming. So instead of just returning one value or a list of value, you can actually return a stream, which will be connected in real time. So I'm showing here a very stupid example in which I have a stream of books. So you could imagine that this, maybe if there is a new book, will just send something to all books. What we do in Haskell is we represent it using Conduit. So that's one of the streaming frameworks in Haskell. So essentially what you get is a sink. A sink is the name in Conduit where you dump the data you want, and then everything you dump there is going to be sent over the wire using the GraphQL subscription. So the same thing of giving all books look a bit like this, where this select sort is coming from the persistent database library. It gives you a conduit, and we just connect this to our sink after some manipulation, this lift server conduit, and then we just pass it there, and it's going to be done for us. Once again, help from the community. We are using Conduit. That's the thing I know the most of, but we would love to be able to be independent of sort of the streaming library. So be able to support pipes, streaming, Streamly, everything you want, but we don't know how to do that. So if somebody knows how to help us here, just you can pop into our Mu Haskell repo and open an issue and start a conversation there. That would be lovely. And then we also have instrumentation. So of course, you are doing this, you want to deploy this. So you may want to do logging, and we support any logging framework essentially, but we tried with Monad Logger and Colog. You can have metrics using this Prometheus server. We have distributed tracing. So actually running your server looks a bit like this. It's ugly, but it all makes sense. So we have to init Prometheus that sets up a few counters in the runtime. And then you run the whole thing, but for running this, because we are using a database where we need to use this with SQLite connection. So that essentially, in this case, is just accessing an in-memory database. Then we have run std error logging, and that adds logging for us to standard error. This is coming from the Monad Logger, which has a wide variety of ways to log. I just showed this in the example because that's like the simplest way and the easiest way when you are testing. And then you run this GraphQL app, which is essentially you give it the port, and then you have your library server. That's the server we just built. We wrap it using Prometheus, so we expose an additional endpoint, which is going to be /metrics. And then all of this is a server which we run. And that's essentially how we try to keep compositionality there. This is all actually also compatible with the WAI framework in Haskell. That's the generic framework for web applications. So if you have like a WAI middleware, you can also inject it here. So you can have additional things. So we try to be as compatible as we can with the rest of the things. So let me take last 5 minutes to talk about how we use type level information. And if you don't know, Haskell, since the future has gotten a huge bump in what you can express at the type level. Actually, everything you can express at the term level can mostly be written, most constant can now be written in the object level, in the type level, sorry. So for example, here we're using type level strings. So that's these quotes there. And also this add, which is type applications to guide what the object is. And instead of having an object with like a normal string, we give it a type level string, and that means that some compile time check is going to be done. So this add things with a quote is actually become strings at compile time, which the compiler can look at and then check that all the object and fields are done. The same happens for object mappings, where we use type level lists. So every time you see a quote, usually that means that there is a type level thing. So we have a type level list where we have a type level mapping, and you have here another quote before the column dash greater than, which is like an arrow. So we have defined our own data type of mappings. That's the column dash arrow thing, and we can use this at compile time and do type level computation to ensure everything is right. And this is something called in Haskell data type promotion. So essentially, every piece of data you can express at runtime, you can promote it and make it available, have it as a compile time thing. It's not that you can, talk to each other easily, but it's like you can use strings and you can create lists and you can create dictionaries at type level, and during compile time, check those dictionaries. So it's like you are doing this computation, you can do your own checks at compile time. That's essentially what we are doing. We are telling the compiler what checks should be done by having type level functions. They are called type families in Haskell, type level functions, and doing some type level computation. And this thing is actually, as I said, heavily used in New Haskell. If you want to see a bit, that's as far as it will fit on the screen, what code this library, this GraphQL does. This is like a dump of what the GraphQL importer does. So it has a type library. I mentioned you're going to create a new type called library, and then it has a bunch of information about, well, you have a package that's called library, that's where the thing resides. And then if you try to make sense of what's happening here, you can see, for example, that there is a service book with an ID which returns a single integer, which is a primitive reference. This is our lingo for just a primitive type. You have a method author. Methods and fields are, because that's sort of in gRPC they are called methods. In GraphQL they are called fields. So we just we have a synonym, but here it just uses the original one, which was called method. And you can see that author returns a single object reference. So that's yet another object in our library server, author. You can go at the end here, and you can see the service query. That's almost at the end. Has an author's method which has one argument, a single argument, which is called name. We have a just because in other service definition languages, you don't have names for arguments. So how do you have an optional thing in Haskell? You use a maybe. So you just use a promote maybe on the type level to say, well, maybe I have a type, maybe I don't. Which also, and then this returns, this single argument is just a text value, and then it returns a list of objects and so on. So all this information, this is here. I mean, this is all type level. This is a type, and as I say, using type level manipulation, you can do your own checks at compiling, which I think it's awesome. I mean, the fact that you can say, well, that's what we should check for a well-formed GraphQL server. That's a check we need to do, and these are actually checked, and you will have a compile time error if they don't. I think that's a great facility in Haskell. If you want to know more, I happen to have a video called "The Inner Workings of New Haskell," where I describe how we build this, and along with my good friend Flavio, we wrote a paper describing our experience doing this. So some of our design choices and some of the pain points we had while developing this in Haskell. That's about the description part. So it's called describing microservices in modern Haskell. So I'm sure you can find it, or just ask me. So if you wanna have a light summary of 7 pages of explanation of how we just stumble wall upon walls, and sometimes we were able to stand up, and sometimes we just we had to change our design because what we thought we'll be able to do with Haskell was not possible. So that's all. I've been talking here about Mu. That's a library to develop microservices. I focus on GraphQL because that's the exciting thing, I think, here. And the other thing I wanted to mention, so apart from GraphQL and the fact that you can see that I'm excited about having something nicer than REST to do queries, is that if you're using Haskell, you can express a lot of information in the type level. And this information might actually come from other sources and import it as we do. But it's very nice to ensure that the app agrees with whatever the contract is. So having said that, I would be really happy to hear about you, not only today, but also you can go into our website, and as I said, everything is open source. So if you wanna try this and then say that your API is terrible, we can try to make it better. We can try to fix some bugs. So that's was it. Thanks for listening. I was hoping that you will have a nice time, but I know you will enjoy the conference. So yeah, that was all.